Thank you for the kind introduction and a very good afternoon to everyone. It is a great pleasure for me to be able to present our work on the world's lowest energy, orthogonally tunable 2.4 GHz transceiver SoC, which exhibits over 3 decades of energy performance scalability for Internet of Things or IoT applications that suffer from highly dynamic channel conditions. Now, today's Internet of Things or IoT as we know it is at the juncture of Moore's law and Shannon's law. Moore's law, up until today, has been enabling cheaper and cheaper computation on smaller form factors through technology scaling, while Shannon's law has continued to increase the channel capacity by supporting high bandwidth communication links. And these two laws together are the keys to enable ever more efficient future systems. But there is a cost of having more computations or supporting higher channel bandwidths, and that comes in the form of power consumption. Therefore, one of the major challenges in designing IoT systems has always been the energy efficiency. And naturally, the question arises, how to reduce the energy consumption in the system? Along with low-power circuit techniques and the inherent advantage obtained from Moore's law, digital systems also leverage energy performance scalability in the form of dynamic voltage and frequency scaling, or DVFS, for reducing the energy for computation. However, in terms of energy performance scalability of communication, a very limited amount of work has been reported in current literature, primarily due to the challenges of reconfiguring RF circuits on the fly. However, reducing the energy for communication is far more important than the energy for computation in a resource-constrained IoT scenario, as today's wireless communication is often 3 to 4 orders of magnitude more costly than computation. This plot is from one of our earlier works, which shows on the x-axis the number of bits switched for computation or the number of bits sent for communication. On the y-axis, we have the energy consumption in joules. As expected, both computation and communication energies, as shown in blue and red respectively, increase monotonically with the number of bits. However, there is always a 1000x to 10,000x gap between the energies for computation and communication for both theoretical and practical implementations, which motivates us to investigate newer methods of reducing the communication energies for longer system lifetime. And that brings us to the outline of this presentation. After a brief introduction, we'll look into some of the existing works on adaptive energy performance scalable communication, followed by the theoretical and circuit level details of the implemented work. We'll present our measurement results and compare our work with the state-of-the-art literature, and finally conclude by summarizing our contributions. As for the introduction, let's look at a traditional IoT example in the form of a wireless body area network or WBAN. The recorded data from the vital signals is sent to a nearby base station, which could be a mobile device or a personal digital assistant. Data from multiple such devices are collected and are further processed at a remote server. Please note that the solid lines in this figure indicate the forward communication channel, while the dotted lines represent the feedback path, most commonly used for sending acknowledgement bits. Data communication in such a network is primarily affected by path loss, SNR in the channel, and network congestion, each of which should be taken care of using different orthogonal strategies. We'll look into all three effects one by one. Firstly, if there is a reduction in path loss between the transmitting and receiving devices due to reduced distances or line of sight communication, the output power or Pout from the transmitter can be reduced to save energy. Alternatively, data rates can be increased, which will complete the transmission in a shorter time, and hence reduce the energy consumption at the same power. Increased path losses will have the opposite effects on Pout and data rate. If the noise in the channel is increased, leading to lower SNR at the receiver, the number of bit errors will increase at the same data rate. Hence, to address this situation, the data rate should be reduced, or certain error correcting codes or ECC should be employed during communication. When multiple mobile base stations are trying to send a large amount of data to the remote server, network congestions can occur. In such a scenario, data rates should be lowered at the sensor node. In the later slides, we shall show a transceiver architecture employing a reconfigurable RF-DAC structure with tapped capacitor matching network that can change the Pout, data rate, or error control coding on the fly and reduce the overall system power as Pout is reduced. We also note that in system level, this problem constitutes an optimization space containing three known dynamic variables: path loss, SNR, and network congestion. Three orthogonally tunable quantities: Pout, data rate, and ECC, and two quantities to be optimized: system BER and system energy. For dynamic path loss, the orthogonal tuning knob of transmit Pout should be utilized, whereas for changing receiver SNR or BER, any of the three tuning knobs can be used. In case of network congestion, only the tuning knob of data rate should be utilized. As we will show later, the maximum Pout achieved in this paper is minus 0.3 dBm or 0.93 milliwatt with 29.3% transmit efficiency. The minimum Pout is minus 13.5 dBm or 0.045 milliwatt with 7.9% efficiency, thereby exhibiting a max to min ratio of about 20x. The symbol rate can be varied from 40 kilosymbols per second to 10 megasymbols per second, while the error control coding or ECC can be turned on for a low receive SNR scenario. The energy per bit is observed to be 79.8 nanojoule per bit at 40 kilosymbols per second minus 0.3 dBm ECC on scenario to 27.6 picojoule per bit 10 megasymbols per second minus 13.5 dBm ECC off scenario, thereby demonstrating a max to min ratio of about 3000x. Moving on, we'll look into some of the prior techniques involving adaptive modulation and coding, supply modulation, and switched capacitor based PA. In adaptive modulation and coding, the order of modulation is increased with increasing amount of available SNR, which increases the spectral efficiency by packing more bits in a symbol. However, the power consumption remains almost constant over different modulations and SNRs. In case of the supply modulated power saving technique, a feedback control loop is applied along with the transceiver that reduces the supply voltage or the on time of the supply according to the requirements. With this, about 40% power savings can be observed, as shown in this CICC2020 work. Here, the RF input power for the receiver is shown in the x-axis, while the y-axis shows the power consumption. Similar results can be obtained with the transmitter as well. This enables event-driven communication with supply modulation. However, the range of the transmit Pout is often very small, since the supply cannot be modulated by a large amount, keeping all devices in proper operating condition. Supply modulation also requires designing of a highly efficient DC-DC converter, as indicated by the left-hand side of this figure. A 6 dB backoff in the overall PA efficiency is realized by operating the PA with 50% of the supply value. Alternatively, a switched capacitor-based approach can be used to realize an implicit high-efficiency DC-DC down conversion at 6 dB backoff by stacking two half-size Class D PA cells, while coupling their outputs with a flying capacitor C-fly. It can be analyzed that the middle point of the two PAs, V-int, is set at 50% of the supply, leading to a 6 dB backoff at the output. Hence, this technique does not require supply modulation and additional DC-DC conversion, but the mismatch between the two PAs can cause nonlinearity issues. The matching network at the output of the PA can also be designed to provide variable terminating impedance to the PA, leading to different power consumptions and Pout. In this work, a Class D PA with a tapped capacitor matching network was used, which exhibited output powers in the range of minus 17 dBm to about minus 2 dBm, as indicated by the x-axis of the right-hand side graph, with transmit efficiencies in the range of 33% to about 5%, as represented by the y-axis. This work also supports multiple modulation schemes such as OOK, BPSK, and GMSK, but does not support higher order modulation such as 16 QAM or 64 QAM. In our implemented work, we wanted to reduce the power consumption of the system as much as possible, at the same time supporting higher order modulation. For that, we first investigated a traditional transmitter supporting higher order modulation schemes. The input bit stream in such an architecture goes through a digital baseband and are divided into in-phase and quadrature paths, as indicated by the red and blue blocks in this diagram. The in-phase path or I path contains an I path DAC and mixer, while the quadrature path or Q path contains separate Q path DAC and mixer. The two paths are combined at the PA, followed by an appropriate matching network or filter, leading to the antenna. Even though the PA is almost always the most power-hungry component in the transmit chain, the mixers and DACs can also consume significant amount of power. To reduce the overall energy, we were interested in replacing all the components inside this gray box with a single RF-DAC based PA, which does the job of the DAC, mixer, and PA simultaneously. In the simplest form of the RF-DAC with OK modulation and a tapped capacitor matching network, we can envision a Class D inverter-based voltage mode PA driving the matching network. However, the maximum Pout in this case can be calculated as VDD squared upon 8ZL, where ZL is the impedance seen by the PA looking at the matching network. If we replace the voltage mode Class D PA with a current mode Class D inverse PA, the maximum Pout can be calculated as VDD squared upon twice ZL, which means that higher Pout can be achieved with the Class D inverse PA for same VDD. This is why we opted for the current mode Class D inverse implementation in this work. For achieving adaptive modulation, we have extended the basic Class D inverse PA into in-phase and quadrature paths, again indicated in red and blue, with differently sized devices that help incorporating the DAC operation into the PA itself. When only the 4X device in the I path is turned on, the RF-DAC based PA works in OK mode. When the 4X device in the Q path is also turned on, we have QPSK. If the 2X devices in both the I and Q paths are turned on as well, we'll have 16 QAM. And if all the 4X, 2X, and 1X devices in both the I and Q paths are turned on, we'll have 64 QAM. The performance is verified using circuit level simulations of TX energy efficiency and transmit efficiency. And the results for QPSK and 64 QAM at 10 megasamples per second is shown here for representational purpose. The leftmost plot shows the output power in the x-axis and energy efficiency on the y-axis for QPSK mode. The different plots represent different supply voltages, and energy efficiencies as low as 30 picojoule per bit can be observed. The second plot from left also shows Pout on the x-axis and energy efficiency on the y-axis, but this time for 64 QAM. The third plot from left shows the transmit efficiency for QPSK on the y-axis and Pout on the x-axis. The highest transmit efficiency achieved is about 31.6%. The last plot shows the transmit efficiencies for 64 QAM, and that also exhibits similar trends. Next, we move to the circuit level implementation details of the reconfigurable SoC. The transmitter has a digital baseband that constitutes of a baseband clock generator, an on-chip pseudorandom bit sequence or PRBS generator, an ECC mapper if error control coding is turned on, and an IQ signal mapper. The input data for test purpose comes from the PRBS generator. Alternatively, real data from a separate sense and compute unit on the chip can also be utilized as input, which can be selected by the baseband select mux. The data rate control is achieved by changing the clock rate from 40 kHz to 10 MHz in 256 steps using an 8-bit control. The ECC can be enabled by one control bit that turns on 8-4 Hamming codes. From the digital baseband, 3 bits of I amplitude control and 3 bits of Q amplitude control determines how many legs of the RF-DAC would be turned on, while 2 bits of LO control generates appropriate local oscillator phases. The power delivery subsystem consists of the previously discussed RF-DAC-based PA and a tapped capacitor-based matching network with reconfigurable capacitor banks. The output power control is achieved using 3 bits that alters the capacitor banks present in the matching network. As mentioned earlier, 3 bits of I path amplitude control and 3 bits of Q path amplitude control determines how many legs in the I path and Q path would be turned on for the RF-DAC. The 2.4 GHz LO generation for both I and Q paths is performed by an on-chip LO generator as shown in the right-hand side of this slide. 4 LO phases are selected based on the 2-bit LO control as obtained from the IQ signal mapper. Along with the transmitter, we also have an ultra-low power OK receiver on the same chip that captures control signals from a nearby base station to achieve closed-loop control on the 8 clock control bits, 1 ECC control bit, and 3 P-out control bits. The receiver consists of 2 stages of RF-LNA, a differential to single-ended converter or D2S, an envelope detector or ED, 2 stages of baseband VGA, and a baseband comparator. For the envelope detector, a 4-stage gate bias structure is used, which increases the output voltage by 4x as compared to the 1-stage envelope detector, thereby compensating for the loss incurred during envelope detection. The SNR, however, remains constant as we increase the number of stages. For the design of the matching network, the effect of finite Q of the on-chip inductor is considered, which modifies the well-known formula obtained in the ideal scenario that considers an infinite Q. 5 different values of C1 and C2 are considered and are put on chip as part of 2 different capacitor banks that cover a matching network impedance from about 100 ohms to about 1600 ohms. While designing the matching network, the effects of pad capacitance, bond-wire inductance, and PCB capacitance are also considered. And the effect of the additional capacitances are included in the value of the on-chip capacitor C1 to obtain the same results as shown in the table provided in the earlier slide. This brings us to the measurement results of the IC. The chip is fabricated in a standard 65 nanometer 1 poly 9 metal process and consumes silicon area of 1.5 mm by 0.5 mm. The measurement setup for the transmitter is shown on the right. The scan codes are provided from a DAC card by National Instruments, while the baseband clock and the 2.4 GHz carrier is supplied by an arbitrary waveform generator. The transmitted output is observed on a spectrum analyzer. For testing the receiver, the RX input is supplied by an arbitrary waveform generator. The final detected waveform is captured on an oscilloscope and is transferred to a PC for BER and ECC calculations. For the default QPSK mode of operation, the transmit efficiency versus output power shows a similar trend as obtained in simulation. The maximum efficiency is observed to be 29.5%, while the maximum P-out is minus 0.3 dBm. The backup efficiency is 19.2% at minus 6.2 dBm and 7.9% at minus 13.5 dBm. The next plot shows the transmitter energy efficiency on the y-axis and symbol rate on the x-axis. The energy efficiency of the transmitter is about 79.8 nanojoule per bit at 40 kSPS and minus 0.3 dBm, while it reduces to 27.6 picojoule per bit at 10 MSPS and minus 13.5 dBm. The max to min ratio of the energy efficiency is about 3000, exhibiting an energy performance scalability for over 3 decades. This plot shows the transmitter energy efficiency on y-axis and P-out on the x-axis. Again, the efficiency numbers are about 9x better than the state-of-the-art due to the simple RF-DAC architecture. The next plot is from the receiver, and it shows the receiver energy efficiency on the y-axis, while the x-axis shows the data rate. For 10 Mbps data rate, the receiver can operate at 13.9 picojoule per bit, making this SoC the most energy efficient transceiver reported in literature, consuming only 41.5 picojoule per bit for both transmit and receive. To observe the effects of ECC, the received signal strength is varied and is plotted on the x-axis of this figure, while the bit error rate or BER is shown on the y-axis. For a BER of 10 to the power minus 3, the sensitivity of the receiver is minus 62 dBm without ECC and minus 67 dBm with ECC at 10 Mbps. In comparison with the state-of-the-art literature, this transceiver SoC demonstrates the lowest TX energy efficiency of only 27.6 picojoule per bit with comparable P-out and data rates, the lowest RX energy efficiency of only 13.9 picojoule per bit, and an energy scalability of about 3000x through reconfigurable data rate, output power, and ECC. The energy performance scalability of 3000x is about 10x higher than the state-of-the-art, And the primary reason behind this benefit is the simple RF-DAC architecture, which is designed in current mode to support higher output power. So in conclusion, this work demonstrates an RF-DAC based transceiver SoC that eliminates the need for I-path and Q-path DACs and mixers for low power consumption. The class D inverse design supports higher output power at lower VDDs, leading to minus 13.5 dBm Pout at 0.8 volt VDD with only 27.6 picojoule per bit efficiency. The SoC also demonstrates 3 orders of energy performance scalability, as summarized in the table. With this, I thank you all for your attention, and I am happy to take questions now. Thank you.